Hey everyone, and welcome to today's Explainer. We're diving into AI2's MolmoAct 2, which was announced on May 5th, 2026. This is a truly major release that's fundamentally changing what researchers can actually realistically test out in physical environments. We are looking at a massive leap forward for open robotics here, really moving away from closed black box systems and toward highly accessible, highly capable foundation models. So it begs the question, are AI robots finally ready to pack up and leave the lab? We're going to explore whether these systems are truly ready for the incredibly messy, chaotic real world, or if, we're just looking at more highly controlled lab demos designed to look perfectly polished for social media. For a long time, the robotic space has been totally dominated by those tightly bounded experiments. But this new release from AI2, it genuinely points to a much faster, much more open future for robotics research. All right, here's our roadmap for today. We're going to meet MolmoAct 2, look at why a 37x speed increase matters, dig into the embodied reasoning backbone, discuss the power of open data, take a hard look at the real-world robotics reality, and finish up with what to watch next. Okay, let's jump right into Section 1, Meet MolmoAct 2, A2's brand new foundation model. Now, crucially, we're not talking about another one of those viral clips where a robot folds laundry in a perfectly staged sequence. No, what A2 actually delivered here is an open foundation model. It's aimed at enabling reusable pipelines and is specifically designed to make robots act much more reliably in physical world manipulation tasks. And because it's open, you, the research community, can actually inspect it, test it, and build entirely new applications right on top of it. Moving right along to Section 2, why 37x faster matters, and how it beats the latency bottleneck. So A2 is reporting that MolmoAct 2 can run up to 37 times faster than their previous MolmoAct system. I mean, 37 times? That is not just a tiny incremental tweak under the hood. That's a total paradigm shift in how quickly the system can process visual information and actually output a physical command. Think about it like this. If a robot has high latency, you get delayed perception. The robot looks at a scene, sends data off to a server somewhere, waits for an answer, and while it's waiting, it's just literally frozen. It's stuck. It's like trying to catch a baseball while you're on a lagging video call. You'd never make the catch, right? By radically reducing that delay between perception and action, you get low latency. The robot becomes responsive. You finally get that real-time fluidity and rapid action that's absolutely required for operating in a dynamic, completely unpredictable human environment. Which brings us to Section 3, the embodied reasoning backbone. Basically, how this model actually thinks. So how exactly does it pull off this incredible speed while still deeply understanding its environment? Well, it all comes down to something called embodied reasoning. For a long time, AI models were mostly just text in, text out. But an embodied AI? It has to comprehend physical space. It must recognize objects, gauge depth, and intuitively grasp the physics of its environment, so it can translate all that into physical actions. It isn't just generating a sentence, it's generating a physical movement in three-dimensional space. Let's peek under the hood at how this two-step process works. In Step 1, AI2 uses Molmo 2ER, which is the embodied reasoning version of their model, to process the visual and physical environment. Then, in Step 2, they pair that reasoning backbone directly with a highly specialized action expert. So the reasoning model basically says, okay, here's the exact layout and what needs to be done, and the action expert takes that and translates it into the precise, raw motor controls for the robot hardware. All right, on to Section 4. The power of open data, and how this fuels independent labs. The real story here isn't just the architecture itself. It's the massive data dump that came right alongside it. Along with the model weights, AI2 released the MolmoAct 2 bimanual YAC dataset. We are talking about over 720 hours of tabletop bimanual robot demonstrations. And just to be clear, bimanual means tasks requiring two robotic arms working together seamlessly, which, if you know robotics, is incredibly complex to map and train. The sheer scale here is what's just wild. As AI2 notes, this is the largest open-source bimanual tabletop manipulation dataset they have ever released. This level of open data creates a massive new playground for the global research community. Independent builders don't have to spend months gathering their own high-quality data just to get to the starting line anymore. When you stack these open systems up against closed, proprietary ones, well, it's a night and day difference. With a closed block box, sure, you might get API access, but you can't actually see the weights. That makes it incredibly difficult to verify claims or adapt the model for custom hardware. But with an open robotics stack, like what A2 is offering, labs get full access to weights and data. Reproducibility becomes highly achievable, and independent researchers can heavily customize the entire system for whatever unique robot they happen to be building.
Okay, time for Section 5, the real-world robotics reality. Let's ground the hype for a second.
Look, before we go declaring that the age of the sci-fi android is fully upon us, we really need a reality check. We have to remember that while zero-shot tasks and tabletop manipulations are incredibly promising, they are still bounded specific test cases. AI2 is reporting very strong results across simulation and real-world zero-shot tasks, absolutely. But a great benchmark does not automatically mean we have a general-purpose household or lab robot ready to go. The real world is messy, it's chaotic, and it's completely unforgiving. Because, let's face it, general-purpose robots are far from solved. We're talking massive physical hurdles here. You have unpredictable safety hazards, like a robot accidentally dropping a heavy tool or misjudging a human's sudden movement. You have incredibly strict hardware constraints and battery limitations. High production costs make scaling a total nightmare. And long-term reliability issues mean a robot that works perfectly for an hour in a demo might completely break down over a month of continuous use. These are deeply rooted physics and engineering problems, and a faster AI algorithm alone cannot magically fix them.
Finally, Section 6, what to watch next and the future of open robotics.
Taking all this in, what should the global AI and robotics community actually be watching for next? Well, first up, we need to see independent benchmark verification. Outside labs really need to test if that up to 37x speed claim actually holds up under completely different, unoptimized conditions. Second, keep an eye on broader hardware adoption. Are independent builders going to easily port the MolmoAct 2ER architecture onto cheaper, off-the-shelf robot arms? And third, we absolutely must track rigorous, real-world safety validation in unstructured spaces, far, far away from controlled tabletops. And I want to leave you with this provocative thought as we wrap up. As AI2 floods the zone with these vital, open datasets, model weights, and incredibly fast architectures, will it be enough? Will it allow independent builders and university labs to actually rival the heavily funded, closed giants of the tech industry? MolmoAct 2 has undeniably moved the starting line way forward, but the race to truly conquer the physical world, that is just beginning. Thank you so much for joining me on this explainer, and, as always, keep questioning what's possible.